Good afternoon, everyone, and thank you for attending our Alternatives to Battery Chemical Fuses in Secondary Safety Circuits webinar. My name is Anton Beck. I'm the Battery Product Manager here at EPIC. Before we get started, I just wanted to let you know that we will be muted during the presentation. If you have any questions as we move along, please enter them into the question panel location in the webinar control panel, and we will try to get to them all before the end of the presentation. If we don't have time to go through them, all your questions will be sure to reply back to you by email. Also, we will be recording the webinar and we'll be posting both the recording and the slideshow on our website and YouTube channel. Our presenter today is Randy Ibrahim. Randy, he's our battery development consultant. Randy has been active within the battery and battery charger industry since 1996. Randy's 30 years of experience in military, medical, industrial, high-volume consumer industries has given him a unique advantage when qualifying battery designs for use in these industries. His work includes pioneering the development of custom safety circuits and battery chargers for unique application and chemistries. As a result, Randy has received numerous patents in his area of work and has written numerous articles for industry trade publications. So without further ado, I will pass it over to Randy.
All right. Thank you, Anton. Really appreciate that. All right. I'm glad everybody could join us today to review the subject, which is a pretty important one. A lot of people believe there's only one alternative to secondary type protection, and we want to make sure that you see other alternatives and other approaches that can be made here. So as I try, oh, there it is. Okay. Computer was not acting up here. The agenda, what we're covering here is to give you a little background here on the secondary safeties and what they are, why they're needed. And then there's 4 methods that are fairly common in meeting the secondary safety requirements. And each one has its merit and trade-offs depending on what your battery design is, what size, what industry that you're shooting for. And then we're going to look at if when are these chemical fuses really a good fit and when are they not? And then when should these FETs be considered as an alternative to the chemical fuses? Some of the pros and cons comparing the two technologies. And also just a quick little at the end of the presentation, how do you use these FET switches? What type of circuits are involved in making it all come together? Here's a little bit of background. First of all, what is a secondary safety? Well, it is exactly how it sounds. It's a secondary safety to the primary safety in a battery pack. The primary safety is there as it sounds. It handles all your real basic safety functions, essentially over voltage for overcharge, that sort of functionality. You have under voltage. If your pack's over discharge, it can cut out, protect the cells. And then also you have overcurrent and sometimes even over and under temperature. And a lot of these primary safeties are use of FET technology in themselves. They're electronic safeties that can be reset if the battery comes back to normal operation. Overall, it protects the cell to be within the operating, what the manufacturers recommend as a safe operating range of an actual cell. So it kind of wraps this electronics around the actual cell. The purpose of the secondary safety is to protect from an overcharge in the event the primary safety circuit fails. This can happen mainly because we are using FETs. FETs do short, they open, you have manufacturing defects. A number of things can go wrong in the overall printed circuit board, and so this is an extra layer of safety in the event if something happens to that primary safety circuit. In the primary, this is really kind of a corner case when secondary safeties are really needed. Mainly if the FET is shorted, something's wrong with the primary safety, and current can go through, and also you have a condition where the charge voltage is too high on the input. Because if your primary safety is essentially shorted and you had proper charging, there's really no danger. You wouldn't want to lose that primary safety, but you can almost picture the secondary safety as a watchdog over the primary safety in the event something happens to it. Now, it is very unlikely that you have an event where your primary safety is not functioning correctly and you have a overcharge condition where your charger's gone awry, or maybe something more common. It would be like a single cell application, like let's say that you have a phone charger where all the charger functionality is in the little wall brick, but right next to it you have another wall brick which is just a 5-volt wall brick. There's no charging function in it. And if by chance they both have the same output connector, you could, or the user could accidentally grab the wrong wall brick without the charging function, plug it in, and being a class 2 type of wall brick, it could have current limiting capability, which would not trip any of your safeties, but you'd have a current coming through your shorted charge FET, and or essentially a primary control safety circuit that's not working properly, and then this could theoretically charge a single cell up to 5 volts, which would be devastating for the technology, which the maximum on most traditional lithium-ion batteries is 4.2 volts. So it would put in a drastic overcharge condition and a risk of potential thermal runaway. The only driving regulations for secondary safeties where we run into primarily would be in the medical field, which is driven by IEC or UL 6601. Now, the UL 6601 calls out UL 2054, and in UL 2054, there are provisions in there when they actually test the safety circuit. They actually will do single point faults. So the first thing the regulatory agency will do is short out from source to drain. They'll short out the charge FET, and then what they'll do is they'll do a slow charge into your circuit with a much higher voltage than what the cell is rated for, and they bring that charge level, the current level, below your current safety trips, and they'll just sit there and see what happens. And with that, it'd be essentially like hooking this current limited power supply directly across the cells, and bad things can happen depending on the cell. And so that's what UL 2054, some of the criteria in there. And also for the IT, the 6950, it also does call out the 2054. Get to same criteria, they'll short out the FETs. And you better have some sort of method, or at least give it some forethought on how you're going to protect that cell in the event that those FETs are shorted out. Another thing is, outside of all the regulatory requirements, we have customers that routinely come to us. They have a very visible product. They definitely want to stay out of headline news. They don't want any possibility of events, so they're willing to add a little extra insurance into each battery by adding a secondary safety circuit. And one note down at the bottom here, it's important to realize that we're in a transition period where they're moving away from UL 2054 and embracing more of the IEC 62133 type testing. In there, it's actually, in my view, I could be wrong, but after reading it, it's a little lax in a lot of ways, because they don't do single fault points. They do some overcharging, but they don't fault out the primary safety. So you wouldn't really need secondary safety if you're testing the 62133. Our general policy is, if it's a mission critical application, and for any of the above reasons, medical or IT or even the customer is driving it, we do put in the secondary safeties as a extra layer of protection. Next, we're going to cover 4 methods. These are very common methods to meet the secondary safety requirements. First thing is, do nothing at all. I mean, that is a possibility. If you select the right cells, you understand, and you're in a close relationship with the cell supplier, sometimes this is a viable method, and there's a good chance that you will pass your test. The next step would be maybe to use a temperature cutoff device. These TCOs, they can actually measure temperature and open up as a thermal fuse and not reset, so it's a one-time type event. Another third common practice is the chemical fuses, and we'll go over a little bit more about what they are and when they're good, and what uses they do serve. And also the fourth method would be to use the FET switch. To do nothing, you really need to understand what's in your cell. A lot of cells, especially the really high discharge cells, they don't have a lot of these safeties built into them. So you need to really understand what cell that you're applying to your application. But essentially, these cells have this internal protection, and one of them is a PTC, as you can see right here, and it's a positive temperature coefficient thermistor in a sense, where if you exceed current, it will heat up and it will open up and reduce current. And then the next internal safety circuit is a CID, which is a current interrupt device. This is much more reliable. And one thing that happens with lithium ion, as you overcharge it, temperature will rise exponentially, and also the internal pressure will rise, increase exponentially as well. And the CID device is like a disc where it senses pressure, and it will open up, and it's like a light switch. It will just interrupt current. It won't allow current in or out of the cell, but the most important thing is it prevents overcharge of the chemistry within the cell. The TCO method, this is a lot more common with single cells, mainly because you really do need to monitor the individual cell, the temperature of each cell, and this becomes, this approach overall becomes less practical in very large packs. But essentially, you have to have the TCO very intimate with the cell. Sometimes you even use a thermal grease or a thermal epoxy under it, and that way it can detect the heat. And sometimes this doesn't work on really large cells because thermal lag, if you look at the larger the diameter or the larger the cell is, you can have rapid heat buildup in the very center of the cell, and it takes physical time for that heat to come out to the outer surface. So you definitely want to look at, when you apply this technology, use it to smaller prismatic, 18650 or smaller, maybe the 21700s might work as well, but that's about the limit. You just don't want to go beyond that, because it kind of defeats the purpose if the internal very center of the cell overheats before the TCO can ever sense temperature. But if it were to trip on a smaller cell, you can see in this diagram here, here's a primary safety circuit. It essentially is like a light switch. It will just go ahead and open up and disconnect or interrupt that current path from the input of the battery into prevent current flowing into the cell. Very simple concept. Chemical fuses, there's kind of a dual purpose here with chemical fuses. They're essentially a regular fuse, but they can be electronically tripped using little internal heaters. And also, they can be tripped from external heat. So if you look down here, if you have a very small circuit board with small FETs and small heat sinking available, copper that you can mount these FETs to the board, sometimes it's wise to be able to measure if these were to get carried away or something malfunctions, and these FETs can overheat, then this chemical fuse can open up and just stop all current flow. When you look at how these chemical fuses are tripped electronically, here's our secondary safety circuit. It's essentially wired in parallel with the primary. The voltage levels of these secondary safeties are slightly higher than the primary safeties, so we always give the primary safety circuit the first opportunity to trip, because it is a resettable type circuit, and we don't want to turn our battery into a brick or an RMA and have it return to the factory. So if it's a mild event or a one-time event and your primary safeties are working properly, we'll go ahead and have those tripped first. They can be reset, and the pack can continue to be used in the field. However, let's say something is wrong with your primary safety and the secondary does have to kick in because it's set for a higher voltage, it will turn on this higher power N-channel FET, and it'll turn on these low resistive heaters here inside your chemical fuse, and as they heat up, they'll clear out this fuse, essentially blow it and stop all current flow going into the pack. A FET switch is very similar in some ways. Yeah, you can set it up as latching or not latching. We still have our primary safety. We have our secondary safety with the voltages set higher than the primary. And essentially, this can just control a FET on and off. And so the way this is drawn is essentially a non-latching method. One of the disadvantages here is if once you turn off the charge current, this cell chemistry is going to relax, and as it drops down the voltage, the secondary safety can reset and essentially allow the charge current to come back into the cell until the lower voltage event happens again. So we're going to look at when chemical fuses are a good fit. Overall, over the years that we've used these, we found that they're better in lower voltage batteries. So we're talking about like a 1 to 4 series lithium ion, so up to like a 12.6, 12.8 volt pack. And there are some out there that you can go a little bit higher in voltage. They're not very common, and they're definitely single source type parts. And so we kind of categorize these as being good for packs in a lower voltage range. Also, if you want to measure the FET overheating temperature that I just showed earlier in the earlier slide, we have the chemical fuse very intimate with the FETs. But this is a really good application because the FET design, FET switches can't do that. And so you kind of get a nice little safety for overheating of FETs. It's a good fit for that. It's not a good fit for most medical applications. If you look at the fine print in just about every company I've seen that supplies these chemical fuses, they do not support medical type applications. So be very cautious of that. Also, when the application uses lower current, these chemical fuses, I've seen some like in the 30 amp range. You can parallel them up some. It gets kind of expensive and kind of tricky. So even below 60 amps, we consider as fairly low current. So they're kind of good in that lower range. Definitely wouldn't see this in an automotive type application. But there's also an exception to the rule. These can be used in a very high current application if you have a separate charge input versus discharge. So if we have a charge path with a separate physical pin on a connector, and that's dedicated to charging, we can run it through smaller FETs, through the smaller chemical fuse, and then the high discharge path would bypass the fuse, and that way it can handle or be able to discharge some of those high currents, and yet still protect for overcharge. And also, where these really shine is in where very low residual currents required, because if you look at it, it's nothing more than a fuse. The only time it becomes active is when you're physically turning on the heaters to blow the fuse. But all its life it's sitting out there in the pack, and it is not using up any energy whatsoever. So it's very good if you have a battery that needs to sit on a shelf for a long, long time, or if you have a battery that's very small in nature, a physically very small amp hour battery, you don't want any extra residual current coming off that safety circuit. So these are sometimes a very good fit for that. Going to the FET switches, essentially balancing this out, we've got a application where you can apply these to very high currents where you have only 2-wire type systems, where you have charging and discharging coming through the same 2 wires but very high current. These shine because we can get hundreds of amps on FETs our size for well over 300 amps, and they can handle the power and the heat dissipation. High voltage applications, these are extremely good for the same reason. We can buy these with very high voltage ratings, and they can protect very multi-100 volt packs without any issue. Another area is medical applications, because there's a lot of cell manufacturers, or not cell, but FET manufacturers out there that do support medical applications. So you just got to make sure that you're sourcing parts from the suppliers that will essentially support medical use. Also multi-sourcing for the same reason. We have up to 10 different manufacturers that make these FETs, so we have a large selection. If a part becomes obsolete or not available, we can switch over to a different manufacturer, drop it in without much problem. So we're never stuck single sourcing parts. What's really nice too is we can reset the safety. The chemical fuse cannot be reset. Once you blow that fuse, it's blown and you have to throw away the pack or have it rebuilt. Here, with some added circuitry, you can go ahead and reset it. Some caution needs to be done there. If it tripped, it may trip for a very good reason. You need to understand that first before you loosely apply that. And then also, one thing we found, sometimes in heat shrink ovens, chemical fuses can do a false trip as the shrink pack is being applied to the pack. That's for any reason. If you have a temperature function on the FET as well, for over temperature, you can turn on your secondary safeties. If you have any of that functionality, what's really nice is at the end of the line during your test, you can do an automatic reset of your FETs, and so your throughput of manufacturing could be improved. So we're going to go into some basic methods. So this is probably a little bit newer here on the FET switch side. Just dive down a little deeper on this. There's essentially two methods here. We can use latching and non-latching. And if you look at it, the secondary safeties, there are a lot of TI parts out there. We also use a lot of Seiko. None of them really latch. They're voltage comparators. If you go above a certain window, there's some hysteresis in there. It will trip and it'll drop a little bit of hysteresis and turn back on. So by its very nature, if you have this configuration with the secondary control, that it will turn on, essentially turn off the FET in the event there's over voltage condition, and turn back on if you don't have a latching mechanism in there. And this is some of the risk. We don't use non-latching. If you have a non-latching, there's some momentum in the chemistry of what we've seen. It's almost like a lag, a voltage lag between charge. So if you're hitting this with some charge, the secondary safety kicks in, it turns off, and the voltage sags a little, and you hit it again. We've seen the voltage creep up a little. And normally this wouldn't be a big deal, but if you're looking at like 100 millivolts overcharge on lithium ion is huge, because normally voltage regulation needs to be within 1%. And so if it doesn't take much to shove this above the 4.2 volts or above the safety 4.35, and now you're risking an overcharge event from happening. So what a much safer approach is to put in the added electronics to latch the output. So once that secondary safety trips, it stays tripped regardless if the voltage sags on the cells, and it will go ahead and keep that FET turned off at all times. And you can see it will slowly drop down in value and stay in a safe voltage range. The best of all worlds that we apply this quite often is a resettable latching safety. So we have it, it latches, but sometimes, let's say some odd event, manufacturing, anything else comes into play where it shouldn't have tripped, and we believe that it's a false trip. This reset can be done manually, or it can be through software control, firmware control, and so just adds a little extra flexibility and prevents scrapping parts. A couple things to consider when developing secondary FET switch protection. It's really important to stay in your safe operating area, and that's also done by looking at your edge times. So especially if the FET's small, this is really important that you don't have localized heating within the die of the FET. So you want to get through those edge times through the linear regions of the FET as quickly as possible, and definitely pay attention to your safe operating area, which is highlighted here in yellow. And sometimes to get those really sharp edge times with a small FET, you need to use some sort of FET driver that can push-pull essentially the charge out of the gate of the FET and get a nice crisp turn on, turn off. Sometimes if you have a larger FET, less current's going through it, it's oversized, turn on times are less important. And there again, you can, there's some trade-offs between the more expensive larger FET and also maybe not having to use a FET driver. And here, another cost reduction that we implement is you really should consider if you using an in-channel FET if the end system allows for it in the negative lead, lifting your ground, and this is better than some of the P-channel on the high side. They're more expensive, they're less efficient. So sometimes it's a pretty good idea to at least entertain it. You don't need a charge pump in there. So there are some definite cost savings in there. Now, this here's a kind of a working example. We developed a 16S battery, and here we have a 57 volt rail, and with the charge pump, it brings it up above the rail about 67 volts to drive all three of these gates. We have discharge FET and a charge FET in here, and then we have our secondary safety FET as well. It's also a very high power 300 amp device, and what we have is essentially some shifting logic in here using some small signal FETs, and then we have the secondary signal down below. If that's pulled low, essentially we are turning off our secondary safety FET, and so then you look at, okay, what on 16S pack, what is driving the signal? And what we have here are 4 of these. This is 1/4, so this covers 4 cells essentially, and these are the actual inputs of the cells. Use just filter caps, and what we do is we actually monitor each individual cell in the pack, and then we come out here. If any one of these exceeds in voltage, we will activate this small signal FET and through this sized impedance, and then our secondary signal is pulled low, and I'll go back to the previous slide. And once this is pulled low, this large secondary FET is turned off. And then if we go further with this, these are all stacked in groups of 4, and what we do is this small impedance here we size accordingly, so we get roughly the same drive. It's definitely a smaller resistor on the top when the circuit's on the very top of the pack. The bottom of the pack is a higher impedance. So just do a quick little summary here. Secondary safety is obviously required per the UL requirements for medical and also IT applications. And also, as I mentioned, sometimes customers want that extra layer of protection because of the sensitivity of their application. So definitely you want to look at that and see if it's right for your use. We covered the 4 methods. Don't rule out, don't do anything. That's actually, we do that quite a bit. We really work closely with our cell suppliers, and a lot of times we can get by without adding all this extra expense. And we have a tendency to lean very heavy towards FET switches. Chemical fuses are difficult to find. You know, in fact, we did a little fire drill the other day trying to locate an older part, and it's getting more and more difficult. So we just almost exclusively use the FET switch. The chemical fuses definitely are a good fit in most non-medical applications. We have used them, but pointed out even on those we're starting to use a lot more of the FET switches, and we have the residual power down to such nanoamps, and some of them are in picoamps, that it really isn't a factor as far as residual current, which obviously where chemical fuses really shine. And then obviously I'm a fan of the FET switches. A lot of our applications are very high current, very high voltage, and we do a whole lot of medical applications, so almost by default, just because of the categories that the type of work that we do, the FET switches definitely shine and have really helped us get to market much faster than some of the chemical fuse alternatives. I'm going to hand this over to Anton. He's the guru when it comes to all our other various products that EPIC provides.
Thank you, Randy. While Randy reviews questions that come in, I wanted to briefly mention some of our additional PCB-based products we offer here at EPIC, such as custom battery packs. You see flex and rigid flex PCBs, high reliability user interfaces, cable assemblies, and our energy efficient fans and motors. Next slide, please. I also mentioned we have facilities all around the globe that specialize in each of these products, such as our Denver, Colorado location for battery pack and power management. User interfaces is down in Largo, Florida, New Bedford, Mass, and Wales, UK for our fans and motors, New Bedford, Mass, Shenzhen, China for our PCBs, flex and rigid flex out of Toronto, Canada, and again, cable assemblies down in Largo, Florida. Our engineering design teams are ready to help our customers create world-class and cost-effective product solutions. Back to you, Randy.
All right, very good. Well, thanks, Anton. Yeah, I was just looking at a couple of these that came through, and I'll start with the first one here. A question came in that said, why not use a PTC in place of a TCO? So if you remember back at the slide that I did a little bit earlier, where you had that single cell and you had a strap, a TCO, sitting intimately against that cell. So the question here is, why not replace a TCO with a PTC? And this is actually really a good question, because one thing a TCO does offer is normally when it breaks, there are some exceptions, but normally when the over temperature event occurs, it clears a fuse. There's absolutely no impedance in there, and there's absolutely no current flow going through the TCO. Unlike if we were to put a PTC in that location, sure, it would trip. It would sense the temperature, external temperature, because the PTCs work through current, they self-heat, and they open up. Also, external temperature can open them up as well. And that's why if you look at a PTC, they're derated. We derate them at 50% at 60 C because of that reason. And so you could use it, but the problem is you're going to get some, as it's stripped open, you're still going to get some small low impedance. It doesn't clear totally. And that small low impedance is enough to trickle charge the cell still, and eventually that cell will overcharge, and it kind of defeats the purpose entirely of a secondary safety. But a good question, and in fact we toyed with that, and we never found the current to get quite down low enough to be able to use them in place of a TCO. Let's see here, on another one, I guess I can kind of pick and choose, can't I? Okay, why does your slide, it says, why does your slideshow show a series fuse in series with the FET? Now I'll just go back, because this one's worth going back on. I put it throughout the whole presentation. What they're referring to here is a fuse, and if you look at the FET switch option, I have the same fuse. The FET's over here, and I could essentially put it down here as well. But this fuse, what's interesting is with a chemical fuse is still a fuse. It has fusing properties. FET switch doesn't. If it fuses, smoke comes out of it, and that's not a good thing. So in order to get that functionality back, and also to be able to cover critical overcurrent events, we do put a fuse in series with the FET, so it acts and behaves a little bit more like a chemical fuse. Yes, a pretty good question there. I should highlight that on the screen. Go back here. Let's see here. Yeah, I think we saw time. Yeah. I'll do one more here. This person asked, he said, towards the end of your presentation, you mentioned that N-channel FETs can be used to reduce costs if used on the ground side of the circuit. Why P-channel FETs? Why are they even used at all with their inefficiencies? Well, very good question. In order to lower costs, we want to get rid of the charge pump, so N channels make sense on on the ground side of the circuit. But we rarely put them there because the majority of the battery packs that we develop, they have fuel gauging on board. And you need to have a reference for your I2C, either SBus or I2C communication back to the host. If you lose that ground, which if you activate a FET will happen, you lose all communication with the battery. So that's our primary reason. We have done some applications where there's no communication, and routinely we'll go ahead and flip, essentially turn off the ground side to save money and overall cost for the product. And also you got to be careful. If you do put it there and you do have communications, you say, oh, no big deal. If it trips, I don't need to communicate. Be very cautious on how you're protecting your I2C lines, because the whole host ground would be pulled up towards the top rail, because ground's all relative. When you get pulled up, its ground is also being pulled up. Make sure that your data lines can handle that. And normally those data lines are a little bit lower in tuning. We use 100 ohm filters in there, and you could exceed their rating easily, especially on a higher voltage pack. So that was also a very good question. So I think we're out of time. So we can, I want to thank everybody for joining us today for this webinar. Hopefully you learned something. Hopefully there's some takeaways here. Please contact what you see on the screen here at sales@epictech.com. If you have any questions, keep your questions coming in. I'll be sure to get to them. We'll respond to all of them via email. And I really want to thank you for your time today.
Thank you, man.